So in this unit, we're going to be looking at thermochemistry, and thermo, like a thermometer, think heat. So thermochemistry is looking at heat transfer, whether heat is being released or absorbed during chemical changes, because it's thermochemistry. It's a subset of thermodynamics. Thermodynamics is the study of heat being transferred in all different situations. So a couple of things that we need to be thinking about. Well, one thing we've discussed before is temperature. Temperature is the measure of the average kinetic energy, the energy of motion in a substance. So if it's a solid, it's how fast are those little molecules vibrating back and forth in place. How fast are the molecules tumbling and moving around in a liquid? How fast are the molecules of the gas zipping around the container? Molecules are going to move around and collide, and faster moving molecules, when they collide, will give energy to slower moving molecules. This is the basis of the first law of thermodynamics. Really, the first law of thermodynamics is that heat cannot be created, or energy is not created or destroyed. It's changed or converted. So I can change energy from the energy of motion into potential energy. I could take energy and put it into a chemical bond. I can crank a roller coaster up to the top of the hill, where all of that energy due to gravity will then get turned into kinetic energy, motion energy, as the people get spun around the track on the roller coaster. Another thing that we will see a lot in this unit is this Greek letter delta. This Greek letter delta is a notation that means change, and that's whether we see it in delta temperature or pressure or volume. Delta always means change. So delta T is a change in temperature. And to get the change in temperature, I subtract the initial from the final. So have a temperature change going from 20 degrees to 40 degrees. Then I do 40 minus 20, initial, final minus initial, and I get that the change in temperature is 20 degrees. That does mean sometimes we can get a negative delta value. What happens if I have a negative delta value? So to look at changes in temperature due to chemical reactions, we have a couple part experiment here, and right now this tube is set up to do part 1. I have 0.4 molar citric acid, 10 milliliters of it, in the bottom of this test tube, and you can see there's a temperature probe in here. And I am measuring the temperature right now to be 24.8 degrees. Okay. I have here a scupula with some sodium hydrogen carbonate or sodium bicarbonate in it. And we're going to put this in and see what happens to the temperature of the mixture using our temperature probe. And so I'm going to move this probe out of the way just a little bit so I can put this in. And you see we get lots of bubbles being formed here. So one question for you is, what is this reaction and what is the gas that's being produced? I'll give you a hint. It is not a flammable gas. It will not burn. So here's the data that the temperature probe collected while the sodium hydrogen carbonate and citric acid were reacting. And this is pretty interesting. We can see that the temperature actually goes down as the reaction starts. So our initial temperature was 24.8 degrees. And then I can go along and look, see if I can get towards, about 50 some seconds where we were towards the end, and it looks like it's about 17.2 degrees for our final temperature. So our initial temperature was 24.8 degrees, and our final temperature is 17.2 degrees. And calculating the change in temperature, remember change is always final minus initial. So that's going to be 17.2 degrees minus 24.8 degrees, which just answered my earlier question about what would it mean if delta T is negative. One thing that can be challenging in thinking about thermochemistry is the difference between the system and the surroundings. Now, chemists always work with the system energy, so we can really think of the system as being the molecules doing a chemical reaction or a phase change. So, for example, if we think about the reaction we just did, the sodium hydrogen carbonate molecules and the citric acid molecules were our system. And we saw that there was a temperature change. Well, what we actually measure is what's happening to the many, many, many water molecules that are surrounding the system. Because there's no way that I can measure a single chemical bond breaking and forming. So I look at the surroundings, what's happening to all of those water molecules, so that I can find out, working back to what's happening in the system. So from our investigation we just did, which had citric acid and sodium hydrogen carbonate reacting, the reaction was spontaneous. It went on its own. I put the two things together and it didn't need any kind of catalyst or spark to get the reaction to go. It generated a gas, and since the gas is non-flammable, you can say, oh, that must have been carbon dioxide. If it had been oxygen or hydrogen, it would have burned. But what we saw was that the solution temperature went down. So the chemicals, the system, must have absorbed energy from the water molecules because the water molecules got slower and lower in energy. The temperature of the surroundings went down. And since energy can't be destroyed, that tells us that the energy went into the system. And that means that what must have happened was when the reactant molecules broke up and became products, those products must be higher energy than my reactants. Let's see if we can get this into a kind of a diagram form. Here I have my reactants down here, the citric acid and the sodium hydrogen carbonate. And they absorbed energy from the water because we got higher energy products, our carbon dioxide, water, and sodium citrate. So we have a name for reactions like this where the products have higher energy than the reactants. Those are endothermic reactions. I like to say it endo, like in. You can hear that N in and N in endo. That's energy going into the system. It is endothermic.
For part 2 of this experiment, we're going to use 3 different sized strips of magnesium, and we're going to see what happens as we change the amount of reactants to how much the temperature changes. So you can see I got the mass of all 3 of the strips. The smallest one is 20 milligrams. The medium one is 34 milligrams. The large one is 49 milligrams. And they've all been polished to bits. They're nice and shiny. Over here I have 3 test tubes set up. They all have 10 milliliters of hydrochloric acid solution in there, and they have 3 separate temperature probes, which will enable me to get the temperature of all of these simultaneously. Okay, so we're going to go ahead and put 1 strip into each of these tubes. And you can see, just like with our gas law experiment, we are generating a gas, hydrogen gas, here.
So here's the temperature data that was collected for our 3 different strips of magnesium. You can see the red line corresponds to the small strip, the blue line to the medium strip, the green line to the large strip. And we can look right now and see what our initial temperature was. For the small strip, our T1, our initial temperature was 26.2 degrees. For the medium strip, it was 25.7 degrees. And for the large strip, it was 25.6 degrees. And then you can see in this case, this was the opposite of the first part where we reacted the citric acid and sodium hydrogen carbonate. Now with the magnesium and hydrochloric acid, we see that in this case, the temperature is increasing. And so let's grab a little spot right here so we can see what the temperatures did towards the end of our data set. And we can see our final temperatures here. Let's use this spot here, get the highest temperature we see. And so I see 35.4 as our final temperature for the small strip, 38.7 as the final temperature for the medium strip, and 43.1 as the final temperature for the large strip. So we see 2 things. All of these did increase in temperature, but what was the effect on the amount of magnesium and the amount of temperature change? And you're going to have to think back to first semester to think about, what does that mean for this heat? Is it an intensive or extensive quantity? So in part 2 of the experiment, we reacted solid magnesium with hydrochloric acid to form hydrogen gas and magnesium chloride solution. And again, this reaction was spontaneous. It started as soon as I put the reactants together. And it again generated a gas. And in this case, it generated hydrogen gas. But when we look at our data, we find that the solution temperature went up, which means the surrounding water molecules, because remember, we are always measuring the surroundings. The surrounding water molecules sped up, because the system, the chemicals, released energy to the water, which means the reactant molecules broke up, and in this case, they must have formed something that had lower energy than the original reactants. If we can think about what this would look like on a diagram, it looks something like this. This is what we call an exothermic reaction. Exo, like exit, energy is exiting the system and warming up the surroundings. So it is an exothermic reaction because products have lower energy than the reactants. And that energy can't just disappear. It has to get transferred into the surroundings, and we see that because the temperature increases. So let's take this and turn it into a new vocabulary term. Let's call this the enthalpy. The enthalpy is the measure of the energy inside the system. In our case, it's a measure of the energy inside our chemicals. And because it's the system, it can never be measured directly, but it can be detected by looking at the change in temperature of the surroundings. If the enthalpy increases, delta H is positive. The final would be larger than the initial. Final minus initial would be a positive number. If the enthalpy decreases, delta H is going to be a negative number. You can see in my option here, if I subtract final minus initial, the final number is smaller than the initial, so I'll end up with a negative number. And enthalpy can be looked at both as a chemical change, as we've been doing in our chemical reactions, but it can also be involved in physical changes, thinking about things like melting or boiling. You know intuitively that that involves energy. Melting ice or boiling water involves putting energy into the water to get it to melt or boil. So if we try and sum this up in terms of reactions, if the energy of reactants is greater than the energy of the products, then delta H, products final minus reactants initial, is going to be a negative number. And this is kind of a downhill reaction. This would be exothermic. So this is an exothermic reaction. Energy is exiting the system. Well, if energy is exiting the system, it cannot just disappear. It has to be changed or converted into the surroundings. So if the system loses energy, the surroundings gain energy, because the energy cannot just disappear. Well, what will I see if the surroundings gain energy? I'll see the surroundings get warmer. So in this case, delta T is going to be positive. I'll have a warmer final temperature because the surroundings get the energy that the system loses. And of course, then we also have the opposite possibility where the energy of the products is higher than the energy of the reactants. This is kind of an uphill situation. In this case, our final minus initial would be a positive number. And we had to increase the energy of the system because our products are higher energy. And that energy can't just appear from nowhere. If the system increases energy, the surroundings have to lose energy to the system. That's where that energy has to come from. And so we'll see the surroundings are going to lose energy. And so that means our change in temperature here is going to be negative. So I hope you're noticing something here that's really very important. the sign of delta H and delta T are inversely related. If delta H is positive, delta T is negative. And if delta T is positive, delta H is negative.